Try this one instead.
Thank you.
Just change back.
Aloha.
The next talk had lots of pretty pictures, fine dust and theoretician. I have a few pictures, and the rest is going to be just pop culture references. Anyway, so I'm going to tell you a little bit about dust, a specific kind of dust, circumstellar dust, dust that is actually formed by stars, very old stars. What kind of stars? The kind of stars that I'll tell you about here. My name is Sundar. By dust, what I mean is solid particles, anything that's a solid. And typically, these dust particles that are formed around these stars have sizes around a micron, around a millionth of a meter, 10,000th of a centimeter. But it ranges. There's a range of sizes, but that you're looking at one little dust particle there. And okay, so I'll first tell you about why at all we should care about dust. And I'll tell you about the two kinds of stars that produce most of the dust in our universe. And then talk about a little bit about, well, now that we know who these people are, talk about how much dust they're producing. And then I'll talk about this problem that we're facing with calculating the dust budget and possible solution to it as well. So why study dust? This is one of my pretty pictures. A beautiful image of a molecular cloud called Rho Ophiuchi. So this is actually an infrared image taken by the Spitzer Space Telescope. What you're seeing here in blue, basically all the blue dots, they are old stars, old sun-like stars. And in the very, very red, you see the very young stars. The reason they're very red is because they're so surrounded by dust that the original light of the star is being reprocessed by the dust. So the dust absorbs light coming in the ultraviolet and the optical, and when it re-radiates this dust, it does it at longer wavelengths, so in the infrared. That's why this is actually about the wavelength at which this light is coming out is about 24 microns, whereas optical light is about a tenth of a micron, maybe 3/10 of a micron or something. Oh, it's 5/10 of a micron. So these are very, very young stars, and the reason they're red is because they're surrounded by dust. And these regions where you kind of don't see anything, it's not there's nothing there, it's that the dust is so dense that you can't even see any emission of 24 microns. So this dust is really, really cold, and it's very, very dense. Right? This is where stars form. So stars form in these molecular clouds. Molecular clouds, by molecular I mean molecular hydrogen. And molecular hydrogen clouds form by collapsing. And in fact, this collapse is sped up by a huge amount by the presence of dust. That's why we need dust. We need dust to form stars. And in fact, dust is not only observed in our neighborhood, in our galaxy, but also nearby galaxies as well. It's not just observed in our galaxy, but also in very, very distant galaxies as well. So we know dust is almost everywhere, right? However, the dust has to come from somewhere. And I'm going to tell you about the fact that the dust actually comes from the stars. So it's sort of a loop we have going on here, that the dust comes from the stars, but the stars need dust to form. So it's sort of a chicken-egg problem. And this is one of the very, very interesting problems in astrophysics that is kind of still unsolved. So this is why people are looking at very, very old galaxies, very, very far away galaxies, to figure out how much dust they have, and to figure out how do you form that dust. So a little bit about the life cycle of dust. What I have here is a beautiful picture. This is an artist's impression, of course. We start in a molecular cloud. So that's this whole thing is a molecular cloud. Individual pockets start collapsing to form stars. Now, depending on your initial mass, and I'm sure if you read a little bit about popular science, you know that the ultimate fate of the star depends on what its initial mass is. So first, I'll talk about the massive stars. By massive stars, I mean anything that has a mass that is greater than about 10 times the mass of the sun. So a massive star over here is so massive that it starts burning hydrogen in its core at a very, very rapid rate. And a huge amount of energy is released, so it looks blue because it's more energetic. eventually it turns into this object called a red supergiant. So basically very, very big, and red because its surface is much cooler than what it used to be. And eventually this red supergiant turns into the famous supernova, which is just an explosion. As part of this explosion, the supernova forms lots and lots of dust. Unfortunately, because the supernova has lots of energetic particles, it also ends up destroying a lot of the dust that it makes, and also the dust around it that existed previously. Anyway, whatever dust that does survive the supernova explosion is eventually sort of ejected away into the surrounding medium, and it's left there to go form some other molecular cloud, be part of some molecular clouds, and eventually form newer stars. What if we had sun-like stars? So anything that's between 1 to 10 times the mass of the sun. You start out looking like our sun. Eventually, you end up as a red giant or an AGB. I'm not going to tell you what AGB stands for. Just think of it like a sun-like, just an old sun-like star. Old sun-like star. So you have again, it's gigantic and it's cool on the surface, but it's not as energetic as a supernova. So when it does die, it has a less spectacular death, but very, very beautiful looking death because it's planetary nebula. So it's outputting its matter, material, into this wispy little cloud that starts shining because of the white dwarf that is at the center over here, this guy. And eventually this wispy little cloud, again, is ejected into the surroundings, which again, form new stars as well. So we have these two prolific sources of dust. This is where all of the material that we are made of comes from, all the solid material, please. So I'm just going to compare them, tell you a little bit, compare and contrast these two guys. Supernovae, like I said, they're very, very massive. So each supernova, on average, produces lots of dust compared to the old sun-like stars. Old sun-like stars are not as massive, so less dust produced per star. However, there are very, very few supernovae in a galaxy like ours compared to the number of old sun-like stars. So this is good for supernovae, but this is bad. So this is the problem. This is why we don't know who wins. In a given galaxy, we don't know who's making more dust. Are the supernova stars making more dust, or are the sun-like stars making more dust? The problem also with supernovae is that they also destroy a lot of dust. Right? So this is the other problem in trying to figure out what the total dust amount is. To make things more complicated, the theory of how much dust is produced and destroyed by supernovae is much more complicated than trying to do this with sun-like stars. So of course, I picked the easy one. I studied the old sun-like stars here. Also, because they're more massive, so a brighter candle burns faster. The more massive supernovae, they only take about 100 million years to end up as an exploding star and generate all this dust. Whereas the sun-like stars typically take at least 10 times that. So about a billion years. So if you started out with a galaxy, if you said started forming stars at this moment, 100 million years from now, you'd have your first. About a few million years from now, you'd start having your first supernovae, and then so the first generation of dust that is built up in your system is going to be from supernovae. But eventually, once these sun-like stars take over, there's going to be a huge spike because they're larger in number. So one specific kind of sun-like star is a carbon star. Why are these guys important? Well, first of all, there's these two beautiful images of carbon stars. This guy is CW Leo, so it's in the constellation Leo. What you're seeing here is that's the central star over there, and these wispy little, almost circular things you see, they're individual epochs of mass loss from the surface of the star. This is an infrared image, so what you're actually seeing is the dust. So these stars are slowly ejecting their mass in the form of gas and dust. In this image, you can see the dust. This one shows a radio image of another star, Ars Scriptoris. In this case, it's the carbon monoxide gas that you're seeing. So this is the gas being ejected, this red stuff over here. Interestingly enough, in this particular case, the ejection forms a spiral. So there are a couple of theories as to why this would happen. The popular one is that it is part of a double star system. So instead of ending up with a concentric shell of mass loss, you end up with a spiral. Anyway, so carbon stars, they produce their own carbon and they're ejecting carbon-rich material in the form of gas and dust into the interstellar medium. So these are old, they're producing carbon in their nuclear processes and then cycling it out to the surface. And carbonaceous dust that is part of this, so soot, graphite, diamond, and silicon carbide as well. They're forming it around the about a few times the stellar radius of these stars. The temperature is cool enough for the gas to solidify to about 1200, maybe 1800, about 1000 Celsius or so. The material solidifies, and then you have the dust shells. This dust is then blown away by the star, and that's what builds up these shells. That's what's happening. The stellar radiation is acting to push out the dust, and eventually this dust is going to be incorporated in forming new stars, and also life. So that's why people say, okay, we are all made of stardust. This is the reason, is that massive stars and to, I think, a larger extent, sun-like stars are putting out all of their material in the form of dust, which eventually helps forming new stars as well. So what I study is, I try to find out, in real-life galaxies, I try to look for these sun-like stars and find out how much dust they're putting out, so doing an estimate. So these are 3 galaxies that my group has been studying. The Large and Small Magellanic Cloud are actually 2 satellite galaxies of our own galaxy, the Milky Way, and they're visible only from the southern hemisphere, Australia. They're extremely beautiful, and of course the southern hemisphere is much better for viewing because there's much less light pollution. The southern hemisphere as well.
Can you use maybe the other mic just to try? Because this is really.
Sorry. I can just yell. Maybe I'll try that. This guy is M33. It's actually visible from the northern hemisphere as well. It's in the constellation of Triangulum. This guy is much more massive than the Large Magellanic Cloud, which is slightly more massive than the Small Magellanic Cloud. This guy actually has beautiful spiral patterns in it. So these are the 3 galaxies that we've been studying for a while, for the past few years, to identify first the sun-like stars, and then try to calculate how much dust they're putting out. So these are all space-based telescope images. These 2 are Spitzer images, and that guy's a Hubble image. So many groups have been doing this, including ours, and we've made these estimates. And what we're trying to do is, because the amount of dust that these guys produce is the input, and the amount of dust absorbed by stars is sort of the output, it's the consumption rate. So we want to find out if these 2 balance out. If they don't, then there may be a problem in the future, as in the consumption might stop, or something of that sort. So we're trying to predict what's going to happen. However, we ended up with this problem when we do this. Not just my group, but many, many groups, 3 or 4 different groups have been doing this for the past 10 to 12 years. And they find that when we calculate the total dust output from all of the stars, not just these sun-like stars, but also including the supernovae, making some sort of back-of-the-envelope estimate of how much dust they put out, we find that the observed mass that we get from the dust is a factor of 50 or 100 less than what we see in the interstellar medium. So this is called the dust budget crisis. We've seen this in many, many nearby galaxies, and perhaps also in our galaxy, although it's more difficult in our galaxy to do this. So where's all this extra dust coming from? Who's making all this dust? It is possible that the problem with making dust in the interstellar medium, in the surroundings, is that it's not dense enough. So around these stars, the old sun-like stars and supernovae, there's not just enough material. So it's not just the high densities, but also the right temperature. In the interstellar medium, it's either too cold or not dense enough. So dust can't actually form there, but you can accumulate more dust once you have the seed particles. So maybe it's possible that there's some processing going on in the interstellar medium, right? But it's a factor of 50 or 100 times that we're missing. So my group was thinking, well, is it possible that maybe we're missing something, right? So this is one of the solutions we have. We've actually observed a couple of very, 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 very dusty stars accidentally. we had these in our data, but the way that the extraction is done, we didn't identify them as stars because they were so red. We thought, no, there's no way that could be a star. These are the dustiest ones are the ones that are also losing the most mass. So if you don't count 10 of them, your total estimate for the total mass lost by a whole galaxy is off by like 50% or something. Right? That's a huge amount. So this is one of the things that the problem is, the reason we miss it is because they're so red, they're so dusty. Even in the infrared, they look like they're very, very cool stars. So we confuse them with newly forming stars. So we have to look for them more carefully. And this is actually what I've been working on for the past few years. And when it comes to it, I'll let you know. I'll maybe give you an update. But yeah, so I'd like to stop here.